Okay, hey everyone. So welcome to the final week of the class. What I want to do today is share with you a few generalizations of reinforcement learning and of MDPs. So you've learned about the basic MDP formalism of states, actions, state transition probabilities, discount factor, and reward. The first thing you see today is two slight generalizations of this framework to state action rewards and to finite horizon MDPs. They'll make it a little bit easier for you to model certain types of problems, certain types of robots, or certain types of factory automation problems will be easier to model with these two small generalizations. So we'll talk about those first. And then second, we'll talk about linear dynamical systems. Last Wednesday, you saw fitted value iteration, which was a way to solve for an MDP even when the state space may be infinite, even when the state space is a set of real numbers or it's Rn, so it's an infinite list of states, so continuous set of states. We use fitted value iteration in which we had to use a function approximator, right, like linear regression, to try to approximate the value function. There's one very important special case of an MDP where even if the state space is infinite, continuous real numbers, there's one important special case where you can still compute the value function exactly without needing to use, like a linear function approximator or to use something like linear regression in the inner loop of fitted value iteration. And so you also see that today. And when you can take a robot or some factory automation task or whatever problem and model it in this framework, it turns out to be incredibly efficient because you can fit a continuous fitted value function as a function of the states without needing to approximate anything. Just compute the exact value function, even though the state space is continuous. So this is a framework that doesn't apply to all problems, but when it does apply, is incredibly convenient and incredibly efficient. So you see that in the second half of today. Oh, yes. One tactical, two tactical things. Let's see, from the questions that we're getting from students, some students are asking us, oh, how is grading in CS229? What if I did well in this, didn't do so well in that? For people taking the class pass-fail, C- or better is a passing grade. This is I think this is standard at Stanford. I think CS229 has historically been one of the heavy workload classes. We know that people taking CS229, yeah, I see a few heads nodding. I think, sorry, people taking CS229 end up putting a lot of work into this class, more, maybe frankly more than average for even Stanford classes. And so we've usually been quite nice with respect to grading, partly, and acknowledge that. So I think yeah, just for what it's worth. So don't sweat too much. Do work hard for the final project, but just don't sweat too much. Oh, and on Wednesday after class, I had a funny question. After I talked about the fitted value iteration question, someone came up to me and said, "Hey, Andrew, this algorithm you just told us, does it actually work? Like, does it actually work on an autonomous helicopter?" And the answer is yes. The algorithms I'm teaching, if you the fit evaluation, as you learned last week, it will work on flying an autonomous helicopter at low speed. So you fly very high speeds, very dynamic maneuvers, crazy bang flipping upside down. You need a bit more than that, but for flying a helicopter at low speeds, the exact algorithm that you learned last Wednesday, as well as any of the algorithms you learned today, including LQR. If you actually ever need to fly an autonomous helicopter for real, these algorithms will actually work decently well, work quite well for flying a helicopter at low speeds. Maybe not at very, very high speeds and at crazy dynamic maneuvers, but at low speeds, these algorithms, pretty much as I'm presenting them, will work. So, okay. So the first generalization to the MDP framework that I want to describe is state action rewards. And so so far, we've had the rewards be a function mapping from the states to the set of real numbers. And with state action rewards, this is a slight modification to the MDP formalism, where now the reward function, R, is a function mapping from states and actions to the rewards. And so, you know, in an MDP, you start from a state S0, you take an action A0, then based on that, you get to S1, take an action A1, take a state S2, get to state S2, take an action A2, and so on. And with a state action reward, the total payoff is written like this. And this is this allows you to model that different actions may have different costs. For example, in the little robot wandering around a maze example, maybe it's more costly for the robot to move than to stay still. And so if you have an action for the robot to stay still, the reward can be, you know, 0 for staying still and a slight negative reward for moving because you're burning or because you're using electricity. Yeah, right. And so in that case, Bellman's equations becomes this: V star equals right, where now you still break down the value of a state as a sum of the immediate reward plus the, you know, expected future rewards. But now the immediate reward you get depends on the action that you take in the current state, right? So this is this is Bellman's equations, and if and notice that previously, you know, we had the max kind of over here, but now you need to choose the action A that maximizes your immediate reward plus your discounted future rewards, which is why the max kind of moved, right? If you look at the equation, or if you look at this equation, I guess the max had to move outside because now the immediate reward you get depends on the action you choose at this step in time as well. So this models that different actions may have different costs. Yeah.
Just to be clear, the max applies to the entire expression, not just the RSA.
Oh, yes. Yes, yes, the max applies to the entire expression, right? Yeah.
So in this reformulation, the rewards are determined with a previous state and action condition, as opposed to sort of like a stochastic based on the next state condition.
Let's see. So in this formulation, the rewards are deterministic based on the state and action. Yes, that is correct. So in this formulation, the reward depends on the current state and the current action, but not on the next state you get to. Right. Right. Okay. Oh, and by the way, there are multiple variations of formulations of MDPs, but this is one convenient one, I guess, the model that different costs. And I think, and actually, and if flying a helicopter, a common formulation of this would be to say that yanking aggressively on the control stick should be assigned a higher cost because yanking the control stick aggressively causes your helicopter to jerk around more, and so maybe you want to penalize that by setting a reward function that, you know, penalizes very aggressive maneuvers. Right? So these are ways. These gives you the as a problem designer sort of more flexibility, right? And then finally, sorry, let me just write this on top. In this formulation, the optimal action. So right. So in order to compute the value function, you can still use value iteration. Right, which is still, you know, V of S gets updated as basically the right-hand side from Bellman's equations. So value iteration works just fine for the state action reward formulation as well. And if you apply value iteration until V converges to V star, then the optimal action is okay, pretty much is just the argmax of that thing. So pi star is just the argmax of this thing. Where now, when you're given state, you want to choose the action that maximizes your immediate reward plus your expected future rewards. Okay. Yeah. So I think just maybe another example. If you want to use an MDP to plan a shortest route for a robot to, say, drive from here in Stanford to drive up to San Francisco, right? Then if it costs different amounts to drive on different road segments because of traffic or because of the speed limit on different roads, then this allows you to say that, well, driving this distance on this road costs this much in terms of fuel consumption or in terms of time and so on, right? So the state action rules. Okay. Yeah. Or in factory maintenance, if you send in a team to maintain a machine, that has a certain cost versus if you do nothing, that has a different cost. But then the machine breaks down, that has yet another cost depending on your actions, right? Okay, so that's the first generalization. The second generalization is the finite horizon MDP. And in a finite horizon MDP, we're going to replace the discount factor gamma with a horizon time t. And we'll just forget about the discount factor. And in a finite horizon MDP, the MDP will run for a finite number of t steps. So you start from state S0, take an action A0, get to S1, take action A1, get to state ST, take an action AT at time step t, and then the world ends, and then we're done, right? And so the payoff is this finite sum. And kind of there's just a full stop at the end of that. You could also apply discounting, but usually when you have a finite horizon MDP, maybe there's no need to apply discounting. And so this models a problem where there are, t time steps, and then the world ends after that, right? Or well, world end sounds a bit dire, but if you're flying an airplane or you're flying a helicopter, and you only have fuel for 30 minutes, right? In an RC helicopter, you might have 20, 30 minutes of fuel. Then you know that you're going to run this thing for 30 minutes, and then you're done. And so the goal is to accumulate as many rewards as possible up until you run out of fuel, and then you have to land, right? So that'd be an example of a finite horizon MDP. Now, and the goal is to maximize this payoff, or the expected payoff over these t time steps, okay? Now, one interesting property of a finite horizon MDP is that the action you take may depend on what time it is on the clock, right? So there's a clock marching from time step 0 to time step t, whereupon the world ends, or whereupon that's all the rewards the MDP is trying to collect. And one interesting effect of this is that this pen isn't that bright. Is that the optimal action may depend on what the time is on the clock. So let's say your robot is running around this maze, and there's a small +1 reward here, and a much larger +10 reward there. And let's say your robot is here, right? Then the optimal action for whether you go left or go right will depend on how much time you have left on the clock. If you have only, 2 or 3 time steps left on the clock, it's better to just rush and get the +1. But if you still have, 10, 20 ticks left on the clock, then you should just go and get the +10 reward, right? And so in this example, pi star of S, it's not well defined because, well, the optimal action to take when your robot is here in this state, should you go left or should you go right? It actually depends on what time it is on the clock. And so pi star in this example should be written instead pi star subscript t of S because the optimal action depends on what time t it is. The technical term for this is that this is a non-stationary policy. And non-stationary means it depends on the time. Actually, it changes over time. Right? Whereas in contrast, up until now, we've been saying, you know, pi star of s is the optimal policy before this formalism, right? We just said pi star of s, and that was a stationary policy. And stationary means does not change. Over time, okay? So one thing that I didn't quite prove, but that was implicit, was that the optimal action you take in the original formulation is the same action, right, no matter what time it is in the MDP. So in the original formulation that you saw last week, the optimal policy was stationary, meaning that the optimal policy is the same policy, you know, no matter what time it is. It doesn't change over time. Whereas in the finite horizon MDP setting, the optimal policy, you know, the optimal action changes over time. And so this is a non-stationary policy. So stationary versus non-stationary just means, does it change over time or does it not change over time? Okay? And so, right. If you're using a non-stationary policy anyway, you can also build an MDP with non-stationary transition probabilities or non-stationary rewards. Non-stationary. Actually, so maybe here's an example. Let's say you're driving from campus, from Palo Alto to San Francisco, and we know that rush hour is at what, like 5 p.m. or 6 p.m. or something, right? And maybe the weather forecast even says it's going to rain at 6 p.m. or something, right? But so you know that the dynamics of how you drive your car from here to San Francisco will change over time. As in the time it takes, you know, to drive on a certain segment of the road is a function of time. And if you want to build an MDP to solve for the best way to drive from here to San Francisco, say, then the state transitions, so ST plus 1 is drawn from state transition probabilities indexed by the state at time t and the action at time t. And if these state transition probabilities change over time, then if you index it by the time t, this would be an example of a non-stationary state transition probabilities. Okay, or alternatively, if you want non-stationary rewards, then you can have R superscript T of SA is the reward you get for taking a certain action, you know, or for being in a certain state at a certain time. Okay, so all of these are different variations of MDPs. And so maybe just a few examples of when you would want a finite horizon MDP or use a non-stationary state transitions. So let's see. If you're flying an airplane, right, for some airplanes, something like for very large commercial airplanes, sometimes over a third of the weight of the airplane comes from the fuel, right? So actually, if you take on a large commercial airplane, you know, when you take off from SFO and you fly to, I don't know where you guys fly to, I don't know, fly to London or something, right, direct flight from here to London. By the time the plane lands, it's actually a much lighter airplane than when you took off, because maybe like a third of the weight disappeared, you know, because of burning fuel. And so the dynamics, how an airplane feels between takeoff and landing is actually different because the weight is dramatically different. And so this would be one example of where the state transition probability changes in a pretty predictable way, right? Already mentioned weather forecasts, right? Where weather forecasts or traffic forecasts, if you're driving here, or if you're driving over different types of terrain over time and you know there's going to rain tomorrow, you're going to know it's going to rain tonight and the ground will turn muddy, you know, then or the traffic will turn bad. And then, I don't know, industrial automation. see a lot of friends work on industrial automation, and I think that maybe one example, if you run a factory 24 hours a day, then the cost of labor, getting people to come into the factory to do some work at noon is actually easier, right, and less costly than getting someone to show up at the factory to do some work at 3 a.m., right? And so depending on really labor availability over time, the cost of taking different actions, and the cost of, and the likelihood of transitioning to different state transition priorities can vary over the 24-hour clock as well, right? And so these are other examples of when you can have a non-stationary policy and non-stationary state transitions, okay? Now, let's talk about how you would actually solve for a finite horizon MDP. And I think for the sake of simplicity, for the most part, I'm going to not bother with non-stationary transitions and rewards. So for the most part, I'm just focused on, for the most part, I'm just going to forget about the fact that this could be varying. I'll mention it briefly, but I want to focus on the finite horizon aspect. So, so let me define the optimal value function. So this is the auto value function for time t for starting in the state S. So this is the expected total payoff. Starting in state S at time t, and if you execute the best possible policy, okay? So now the optimal value function depends on what time it is. Because if you look at that example of the +1 reward on the left and the +10 reward on the right, depending on how much time you have left on the clock, the amount of rewards you can accumulate can be quite different, right? If you have more time, you have more, then you can more time to get to the +10 reward in the +1 and +10 reward that I drew, example that I drew just now. And so in this example, value iteration becomes the following. It actually becomes a dynamic programming algorithm, which you see in a second, okay? Which is that, let's see. Shoot, all right, I think I need 3 lines. Let me just do this here. All right, which is that V star of t of S is equal to max over A R of SA plus okay. Actually, this is a question for you. So there's one missing thing here, right? So we're saying that the optimal value you can get when you start up in state S at time t is the max over all actions of the immediate reward plus sum of S prime, state transition rate S prime times V star of S prime, and then what should go in that box? Okay, cool, awesome, great. Right? And then pi star of S is just, arg max of A, right, of the same thing, of this whole expression up on top. And so this formula defines Vt as a function of Vt plus 1. So this is like the iterative step, right? Given V10, you can compute V9. Given V9, you can compute V8. Given V8, you can compute V7. And so to start this off, there's just one last thing we need to define, which is V capital T at the finite step, at the final step, when the clock's about to run out. All you get to do is choose the action A, that maximizes the immediate reward, and then there's no sum after that, right? So if you start off at state S at the final time step T, then you get to take an action and you get an immediate reward, and then there is no next state because the world just ends right after that step, which is why the auto value at time T is just max over A of the immediate reward, because what happens after that doesn't matter, okay? So this is a dynamic programming algorithm in which this algorithm, this step on top, defines, allows you to compute V star of T. And then the inductive step, or the n+1 step, I guess, is if you then, having computed V star of T for every state S, right? So you compute this for every state S. Having done this, you can then compute V star T minus 1 using this inductive step. Then V star T minus 2, and so on, down to V star of 0. So you compute this for every state. And then based on these, you can compute, to pi star of T, right? Compute the auto policy, the non-stationary policy for every state as a function of both the state and the time. Okay? All right, cool. And I think, again, I don't want to dwell on this, but if you want to work with non-stationary state transition probabilities or non-stationary rewards, then this algorithm hardly changes in that you can just add, if your rewards and state transition probabilities are indexed by time as well, then this is just a very small modification to this algorithm. And it turns out that once you're using a finite horizon MDP, making the rewards and state transition probabilities non-stationary is just a small tweak, right? So you could, yeah. Can you say that again? This one? Oh, a non-stationary. So in the end, you get a policy pi star subscript T of S.
So?
I'm sorry. Oh, this one? Oh, this one? Oh, I see. Sure. Yes. Oh, a pi star. This is a non-stationary policy. Yes. Oh, that's what I meant. Yeah. So yeah. So this the auto policy will be a non-stationary policy. Yes. I think I was using pi star to not to denote that it has to be a fixed function of time. But yes, that's a non-stationary policy. Thank you. Yeah. Right. If you take big T to infinity, can this become the usual value iteration? Let me think. So there are two things with that. So the two frameworks are closely related, right? You can kind of see the relationship between the valuation. One problem with taking this framework to big T to infinity is that the values become unbounded, right? As in, yeah, and that's actually one of the reasons why we use the discount factor when you have an infinite horizon MDP, when the MDP just goes on forever. One of the things the discount factor does is it makes sure that the value function doesn't grow without bound, right? And in fact, if the rewards are bounded by by some Rmax, then when you use discounting, then V, is bounded by, I guess, Rmax over 1 minus gamma, right? By the sum of a geometric sequence. And so, but in the finite horizon MVP, because you only add up T rewards, it can't get bigger than T times the Rmax. Yeah.
So this seems like in our robot example, if we were looking at just one V star for specific T, that we would see kind to get it, you'd have a larger reward, otherwise you have a very small one. But like intuitively, I'm not seeing where you would have like a very abrupt change in this algorithm. It seems like it would still be sort of like a smooth updating.
Let me think. So I think that, boy, so I think, you know, what you find is that, let's see. Actually, let me just draw a 1D grid just to make life simpler, right? So let's say there's a +1 reward there, and a +10 reward there. If you look at the optimal value function, depending on what time it is, if you have 2 times, and let's say the dynamics are deterministic, right? So there's no noise. Then if you have 2 time steps left, then I guess V star would be, you know, 10, 10, 10, 1, 1, 1, 0, 0, 0, right? And so depending on where you are, I guess if you're, yeah, actually, in fact, I guess if you're here, there's nothing you can do, right? You just can't get to either reward in time. But depending on whether you're here or here or here, the optimal action will change if you compute what is pi star. Does this make sense?
Yeah, that's fine.
Oh, okay, cool. Yeah, maybe do encourage you to, if this, yeah, if you actually build a little, you know, grid simulator and use these equations to compute pi star and V star, you will see that the optimal policy, when you have lots of time, will be this. Wherever you are, go for the 10 reward, but when the clock runs down, then the optimal policy will end up being a mix of go left and go right. All right, cool. Hope that was okay, yeah. All right. So, so the last thing I want to share with you today is linear quadratic regulation. And as I was saying at the start, LQR applies only in a relatively small set of problems, but whenever it applies, this is a great algorithm, and I just, you know, use it whenever, right? It seems useful to apply because it is very efficient and sometimes gives very good control policies. And let's see. And so LQR applies in the following setting. So let's see. In order to specify an MDP, we need to specify the states, the actions, the state transition probabilities. I'm going to use the finite horizon formulation, so capital T and the reward. This also works with the discounted MDP formalism, but this would be a little bit easier, a little bit more convenient to develop with the finite horizon setting. So let me just use that today. And LQR applies under a specific set of circumstances, which is that the set of states is in Rn, set of actions is in Rd, and so to specify the state transition probabilities, we need to tell you what's the distribution of the next state given the previous state. So to specify the state transition probabilities, I'm going to say that the way st plus 1 evolves is going to be as a linear function some matrix A times st plus some matrix B times at plus some noise. And sorry, there's a little bit of notation overloading again. Sorry about that. A is both the set of actions as well as this matrix A, right? So there's two separate things, but same symbol. I think that the field of a lot of the ideas from LQR came from traditional controls. From I guess from double E and mechanical engineering. A lot of the ideas from reinforcement learning came from computer science. So these two literatures kind of evolved, and then when the literatures merge, you end up with clashing notation. So CS people use A to denote the set of actions, and so, you know, mechanical engineering and double E people use A to denote this matrix. And when we merge these two literatures, the notation ends up being overloaded. Right? Okay. Oh, and then it turns out one thing we'll see later is that this noise term, we'll see later, is actually not super important. But for now, let's just assume that the noise term is distributed Gaussian with some mean 0 and some covariance sigma subscript w. Okay? But we'll see later that the noise will be less important than you think. Right. And so this matrix A is going to be R n by n, and this matrix B is going to be R n by d, where n and d are respectively the dimensions of the state space and the dimension of the action space. So for driving a car, for example, we saw last time that maybe the state space is 6-dimensional. So if you're driving a car, maybe the state space is x, y, theta, x dot, y dot, theta dot. And the action space is steering control. So maybe A is 2-dimensional, right? Acceleration and steering, right? Okay, so let's see. So to specify an MDP, we need to specify this 5-tuple, right? So we specified 3 of the elements. The fourth one, T, is just some number, right? So that's easy. And then the final assumption we need to apply LQR is that the reward function has the following form. That the reward is negative of S transpose US plus A transpose VA, where U is n by n, V is d by d, and UV are a positive semi-definite. Okay, so these are matrices bigger than 0, so positive semi-definite. Okay. So the fact that U and V are positive semi-definite, that implies that STUS is greater than or equal to 0, and S transpose US, sorry, A transpose VA is also greater than or equal to 0. Okay. So here's one example. If you want to fly an autonomous helicopter, and if you want, the state vector to be close to 0. So the state vector captures the position, orientation, velocity, angular velocity. If you want a helicopter to just hover in place, then maybe you want the state to be, regulated or to be controlled near some 0 position. And so if you choose U equals the identity matrix, and V also equal to the identity matrix, these would be different dimensions, right? This would be an n by n identity matrix. This would be a d by d identity matrix. Then R of SA ends up equal to negative norm of S squared plus norm of A squared. Okay? And so this allows you to specify a reward function that penalizes, with a quadratic cost function, the state deviating from 0, or if you want, the actions deviating from 0, thus penalizing very large jerky motions on the control sticks. Or if you set V equal to 0, then the second term goes away. Okay, so these are some of the cost functions you can specify in terms of a quadratic cost function. Okay. Now again, just so that you can see the generalization. If you want non-stationary dynamics, this model is quite simple to change, where you can say the matrices A and B depend on the time t. You can also say these, the matrices U and V depend on the time t. So if you have non-stationary state transition probabilities or non-stationary cost function, that's how you would modify this. But I won't use this generalization for today. Okay. Now, So the two key assumptions of the LQR framework are that first, the state transition dynamics, the way your states change, is as a linear function of the previous state and action plus some noise. And second, that the reward function is a quadratic cost function, right? So these are the two key assumptions. And so first, where do you get the matrices A and B? One thing that we talked about on Wednesday already was, so again, this will actually work if you're trying to apply LQR to flying an autonomous helicopter. This will work for a helicopter flying at low speeds, which is if you fly the helicopter around, start to some state S0, take an action A0, get to state S1, do this until you get to ST, right? And then this was the first trial. And then you do this m times. Right, so we talked about this on Wednesday. So fly the helicopter through m trajectories of t time steps each. And then we know that we want st plus 1 is approximately ast plus bat. And so you can minimize right? So we want the left and the right-hand side to be close to each other, so you could, minimize the square difference between the left-hand side and the right-hand side in a procedure a lot like linear regression in order to fit matrices A and B. So if you actually fly a helicopter around and collect this type of data and fit this model to it, this will work. This is actually like a pretty reasonable model for the dynamics of a helicopter at low speeds. Okay, so this is one way to do it. So let's see, method one is to learn it, right? A second method is to linearize a nonlinear model. So let me just describe the ideas at a high level, which is, let's say that, and I think for this it might be useful to think of the inverted pendulum, right? So that was so imagine you have inverted pendulum. That was that, right? You have a pole, and your long vertical pole, you're trying to keep a pole balance. So for an inverted pendulum like this, if you download an open source physics simulator, or if you have a friend, with a physics degree, help you derive the Newtonian mechanics equations for this. Let's see. I actually tried to work through the physics equations for inverted pendulum ones. It's pretty complicated, actually. I don't know. But you might have a function that tells you that if the state is a certain position, orientation of the pole, velocity, angular velocity, and you apply a certain acceleration, the action is accelerate left or accelerate right, then 1/10 of a second later the state will get to this, right? So your physics friend can help you derive this equation. And then maybe plus noise, right? Well, let me just ignore the noise for now. And so what you have is a function right, that maps from the state, xx dot theta, theta dot, that's the position of the cart and the angle of the pole, and the velocities and angular velocities that maps from the current state at time t, comma at, right, maps from the, I guess, current state vector to the next state vector as a function of the current state and current action. Okay, so here's what linearization means, and I'm going to use a 1D example. So because I can only draw on a flat board, right? I can't, because of the two-dimensional nature of the whiteboard, I'm just gonna use a, let's suppose that you have st plus 1 equals f of st, and let me just ignore the action for now. So I have one input and one output, so I can draw this more easily on the whiteboard. So if you have some function like this, so the x-axis is st, and the y-axis is st plus 1, and this is the function f, right? We'll plug in back the action later. What the linearization process does is you pick a point, and I'm going to call this point st over bar, and we're going to take the derivative of f and fit a straight line. Sorry, I'm not drawing a straight line very well. Take the tangent straight line at this point, st bar, and and we're going to use this straight line. Actually, let's draw that in green. Right. And we're going to use the green straight line to approximate the function f. And so if you look at the equation for the green straight line, the green straight line is a function mapping from st to st plus 1. And s bar is the point around which you're linearizing the function. So s bar is a constant. And this function is actually defined by st plus 1 is approximately the derivative of the function at s bar times st minus s bar plus f of s bar t. Okay, and so s bar t is a constant, right? And this equation expresses st plus 1 as a linear function of st. Okay. So think of s bar t as a fixed number, right? It doesn't vary. So given some fixed s bar, this equation here, this is actually the equation of the green straight line, which is it says, if you use a green straight line to approximate the function f, this tells you what is st plus 1 as a function of st, and this is a linear or an affine relationship between st plus 1 and st. Okay? So that's how you would linearize a function. And in a more general case, where and in a more general case where st plus 1 is actually a function of, putting this back in, right, both st and at, the formula becomes, let me see, well, I'll write out the formula in a second. But in this example, s bar t is usually chosen to be a typical value for s, right? And so in particular, if you expect your helicopter to be doing a pretty good job hovering near the state 0, then it'd be pretty reasonable to choose s bar t to be the vector of all zeros. Because if you look at how good is the green line as an approximation of the blue line, right? In a small region like this, the green line is actually pretty close to the blue line. And so if you choose s bar to be the place where you expect your helicopter to spend most of its time, then the green line is not too bad an approximation to the true function, to the physics. Oh, excuse me, or if you expect for the inverted pendulum, if you expect that your inverted pendulum will spend most of its time with the pole upright and the velocity not too large, then you choose s bar to be maybe the 0 vector. And so long as your pendulum, your inverted pendulum, is spending most of its time kind of close to the 0 state, then the green line is not too bad an approximation for the blue line, right? So this is an approximation, but you try to choose because I mean, in this little region, it's actually not that bad an approximation. It's only when you go really far away, right, that there's a huge gap between the linear approximation and the true function f. Okay. All right. And so in the more general case where f is a function of both the state and the action, then what you have to do is the input now becomes st comma at, because f maps from st comma at to st plus 1. And then instead of choosing s bar t, you're choosing s bar t comma a bar t, which is a typical state and action around which you linearize the function. Let me just write down the formula for that. In which you would say, if you linearize f around a point given by s bar t, a bar t, kind of the typical values, then the formula you have is st plus 1 is given by f of s bar t, a bar t, plus the gradient with respect to s transpose st minus s bar. Okay, so this is the generalization of the 1D function we measured just now, we wrote down just now, which says that the next state is approximately this point around which you linearize, plus the gradient with respect to s times how much the state differs from the linearization point, plus the gradient with respect to the actions times how much the action varied from a bar. Okay? And this kind of generalizes that equation you wrote. So this equation expresses st plus 1 as a linear function, or technically an affine function, of the previous state and the previous action, right, with some matrices in between. And from this, after some algebraic munging, you could re-express this as st plus 1 equals ast plus bat. And just there's just one other little detail, which is you might need to redefine st to add an intercept term. Right, and because it's an affine function with an intercept term rather than a linear function. But so from this formula, with a little bit of algebraic munging, you should be able to figure out what are the matrices A and B, but you might need to add an intercept term to the S, but this is just an affine function. You can rewrite in terms of matrices A and B. Okay? All right. So, right, I hope that makes sense, right? That this linearization thing, expresses st plus 1 as a linear function of st and at, right? This is just a linear, it's just the way st plus 1 varies, it's just some matrix times st, some matrix times at, and that's why with some munging you can get into this formula for some matrix A and B, okay? But because there's some constants floating around as well, like this, you might need an extra intercept term to multiply into A to give you that extra constant. But where we are, we now have that for these MDPs, either by learning a linear model with the matrices A and B, or by taking a nonlinear model and linearizing it, like you just saw, you can model, hopefully model an MDP as a linear dynamical system, meaning this, st plus 1 is this linear function of the previous state in action, as well as hopefully with a quadratic reward function, or right, in the form that we saw just now. So let me just summarize the problem we want to solve. AST, oops, sorry. ST plus 1 equals AST plus BAT plus WT. So this is a noise term. And then R of S A equals negative S transpose US plus A transpose VA. Right? And this is the final horizon MDP, so the total payoff is R of S0, A0 plus dot 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 plus R of ST AT. Okay? So, let's figure out the dynamic programming algorithm for this. The remarkable problem, the remarkable property of LQR, and what makes this so useful is that if you are willing to model your MDP using those sets of equations, then the value function is a quadratic function, right? And so let me show you what I mean. And so if your MDP can be modeled as this type of linear dynamical system with a quadratic cost function, then it turns out that V star is a quadratic function, and so you can compute V star exactly, right? So let me show you what I mean. We're going to develop a dynamic programming algorithm to compute the optimal value function V star. Similar to what we did a little earlier today with the finite horizon MDP with a finite set of states, let's start with the final time step, and it will work backwards. So V star T of ST is equal to max over AT of R of ST AT. This is max over AT of negative right? But this is always greater than or equal to 0 because V is positive semi-definite. And so the optimal action is actually to just choose the action 0. And so the max over this is equal to negative ST transpose UST, right? Because V is a positive semi-definite matrix, this thing is always greater than 0. And so this tells us also that pi star at the final action is the argmax. So the optimal action is to choose, the vector of 0 actions at the last time step. Okay? So this is the base case for the dynamic programming step of value iteration, where the optimal value at the last time step is just choose the action that maximizes the immediate reward, which means maximize this, right? And this is maximized by choosing the action 0 at the last time step. Okay? Now, I feel like these blue pens keep, let's see if there's anything back. Ooh, okay. Now, the key step to the dynamic programming implementation is the following, which is suppose that V star T plus 1, ST plus 1, is equal to a quadratic function right? Okay. So in the
Just to back up, why did you treat the inline equation the right-hand side to be critical? So would you say the same thing about the other term? Because you had said that both of them were primitive semi-definites. So S transpose U, S is also relevant.
yes, it's true that this term is also greater than 0, without the minus sign, right? Without the minus sign, that term is positive, and so, but you only get to maximize with respect to AT. right? So the best you could do for this term is set it to 0. Yeah, thank you. Right, cool, thank you. All right. Now for the inductive case, we want to go from Vt plus 1, V star t plus 1, to computing V star t, right? And the key observation that makes LQR work is, let's suppose V star t plus 1, the optimal value function at the next time step, let's suppose it's a quadratic function. So in particular, let's suppose V star t plus 1 is, this quadratic function, parameterized by some matrix, this capital phi t plus 1, which is an n by n matrix, and some constant offset psi, which is a real number. What we'll be able to show is that if you do one step of dynamic programming, if this is true for V star t plus 1, that Vt, after one step, as you go from V star t plus 1 to Vt, that the optimal value function Vt is also going to be a quadratic function with a very similar form, right? With I guess, t plus 1 replaced by t, right? And so in the dynamic programming step, we are going to update Vt st equals max over At r of st comma At plus, and then, I think you remember, right, previously, well, let me write this in green. Previously, we had sum over s prime, oh, actually, st plus 1, I guess. So we st, At, st plus 1, v star, t plus 1, st plus 1. So that's what we had previously when we had a discrete state space and we're summing over it. But now that we have a continuous state space, this formula becomes expected value with respect to st plus 1 drawn from the state transition probabilities of v star p plus 1 st plus 1. Yeah, I think that looks right. Okay. So the optimal value when the clock is at time t is choose the action A that maximizes the immediate reward plus the expected value of your future rewards when the clock has now ticked from time t to time t plus 1, and you're in state st plus 1 at time t plus 1. Right? So let's see. So this is a pretty beefy piece of algebra to do. I feel like showing this full result is, I don't know, is like at the level of complexity of a typical CS229 homework problem, which is quite hard. But let me just show the outline of how you do this derivation and why this inductive step works, right? But I think but if you want, you could work through the algebra details yourself at home. Which is that, actually, let me do this on the next board. So V star t of st is equal to max over At of the immediate reward, right? So that's the immediate reward, and then plus the expected value with respect to st plus 1 is drawn from a Gaussian with mean ast plus bat and covariance sigma w. So remember, st plus 1 is equal to ast plus bat plus wt, where wt is Gaussian with mean 0 and covariance sigma w. Right? So if you choose an action at, then this is the distribution of the next state at time t plus 1. And then expected value of this quadratic term. Because this quadratic term here, kind of in the inductive case, was what we showed was v star for the next time step, right? So it turns out that, let's see, so this is a quadratic function, and this expectation is the expected value of a quadratic function with respect to s drawn from a Gaussian, right, with a certain mean and a certain variance. So it turns out that the expected value of this thing, right, well, this whole thing that I just circled, this thing simplifies into a big quadratic function of the action AT, right? And then, and so in order to, derive the argmax, or to derive v star of s, you would derive this big quadratic function, take derivatives with respect to at, set to 0, right, and solve for at. Okay. And if you go through all that algebra, then you end up with the formula for at as follows. Okay. And I'm going to take that big matrix and denote that LT. Okay. Oh, and so this shows also that pi star at time t of st is equal to LT times st. Okay. So the takeaway from this is that under the assumptions we have, right, linear dynamical systems with quadratic cost function, the optimal action is a linear function of the state st, right? And this is not a claim that is made through function approximation. I'm not saying that you could fit a straight line to the optimal action, and if you fit a straight line, that you get this linear function, right? That's not what we're saying. We're saying that of all the functions anyone could possibly come up with in the world, linear or nonlinear, the best function, the best action is linear. So there is no approximation here, right? So it's just that, it's just a fact that if you have a linear dynamical system, the best possible action at any state is going to be a linear function of that state, right? So we haven't approximated anything, right? Let me see. Yeah, all right. Let me write this here. And then the other step is that if you take the optimal action and plug it into the definition of V star, then by simplifying, which again is quite a lot of algebra, but after simplifying, you end up with this equation. Where, again, I'll just write out the formulas, just, So to summarize the whole algorithm, right? Let's put everything together. And so what these two equations do is they allow you to go from v star t plus 1, which is defined in terms of phi t plus 1 and psi t plus 1, and it allows you to recursively go back to figure out what is v star t using these two equations, right? So phi t depends on phi t plus 1, psi t depends on phi t plus 1 and psi t plus 1. And this sigma w, this is the covariance of wt, right? The sigma subscript w. This is not a summation over w. This is a sigma matrix subscripted by w. That was a covariance matrix for the noise terms we were adding on every step in our linear dynamical system. Okay, and this is a trace operator, sum of the diagonals. Okay. So just to summarize, here's the algorithm. You would initialize phi t to be equal to negative u and psi t equals 0. And so, you know, that's just taking this equation and mapping it there, right? So the final time step, those two, oh, sorry, it should be capital T, right? So that, those two equations, for phi and psi, it defines v star of capital T. And then you would, you know, recursively calculate phi t and psi t using phi t plus 1 and psi t plus 1. So you go from, you know, for t equals t minus 1, t minus 2, and so on, and go backward, count down from, right, t minus 1 to t minus 2, and so on down to 0. Calculate LT as above, right? And LT was a formula, I guess, we had over there saying how the optimal action is a function of the current state depending on the A and B and phi. And then finally, pi star of ST equals LT of ST. Okay? And this algorithm, the remarkable thing, one really cool thing about LQR is that there is no approximation anywhere, right? You might need to make some approximation steps in order to approximate a helicopter as a linear dynamical system by, you know, fitting matrices A and B to data, or by taking a nonlinear thing and linearizing it. And you might need to just restrict your choice of possible reward function that's quadratic. But once you've made those assumptions, none of this is approximate. Everything here is exact. Right? Question?
So at the beginning, we were approximating S2 plus 1 with the linear function. So that is the approximation.
Yes, that's right. Yep, yeah. So the approximation steps needed are getting your MDP into the form of a linear dynamical system with a quadratic reward. So that is approximate. But once you specify the MDP like that, all of these calculations were exact, right? So we're not approximating the value function or quadratic function. Is that the value function is a quadratic function, and you're computing it exactly. And the optimal policy is a linear function, and you're just computing that exactly. Okay. I want to mention, before we wrap up, I want to mention one unusual fun fact about LQR, and this is very specific to LQR, and it's convenient, but let me say what the fact is, and just be careful that this doesn't give you the wrong intuition, because it doesn't apply to anything other than LQR, which is that if you look at where, so first, if you look at the formula for L, let me see. Move this around. All right. If you look at the formula for LT, you need to compute. I mean, the goal of doing all this work is to find the optimal policy, right? So you want to find LT so you can compute the optimal policy. You notice that LT just depends on phi but not psi, right? So, and maybe this kind of makes sense. You're going to, when you take an action, you get to some new state, and your future payoffs is a quadratic function plus a constant. It doesn't matter what that constant is, right? And so in order to compute the optimal action, in order to compute LT, you need to know phi, or actually phi t plus 1, but you don't need to know what is psi t plus 1, right? Now, if you look at the way we do the dynamic programming, the backwards recursion, what if you implement a piece of code that doesn't bother to compute psi, right? So these are the two equations you use to update phi and psi. But what if, let's say you delete this line of code, just don't bother to compute it. And just don't bother to compute that, and don't bother to compute that, right? So you notice that phi depends on phi t plus 1, but it doesn't depend on psi. And so you could implement the whole thing and compute the optimal policy and compute the optimal actions without ever computing psi, right? Now, the funny thing about this is that the only place that sigma w appears is that it affects only psi t, right? So, if we do what I just cross out in orange and just don't bother to compute psi t, then the whole algorithm doesn't even use sigma w, right? So one very interesting property of the LQR, of this formalism is that the optimal policy does not depend on sigma w, right? And I think maybe this is so V star depends on sigma w, because if the noise is very large, if there are huge gusts of wind blowing your helicopter all over the place, then the value would be worse. But pi star and LT do not depend on sigma w, okay? So this is a property that's very specific to LQR. Don't overgeneralize it to other reinforcement learning algorithms. But this, I think the intuition to take from this is, first, if you're actually applying the system, don't bother to don't try too hard to estimate sigma w, because you don't actually need to use it, which is why when we're fitting a linear model, I didn't talk too much about how you actually estimate sigma w, because in an LQR system, it literally doesn't matter in a mathematical sense in terms of what is the optimal policy you compute. And then the second, there may be slightly useful intuition to take away from this is that for a lot of MDPs, if you're building a robot, remember to add some noise to your system, but the exact noise you add doesn't matter as much as one might think. So what I've seen in working with a lot of robots, a lot of MDPs is, do add some noise to your system and make sure your learning algorithm is robust to noise. And the form of the noise you add, it does matter. I don't want to say it doesn't matter at all. I mean, in LQR, it doesn't matter at all. For other MDPs, it does matter. But I think the fact that you're remembering to add some noise is often, in practice, more important than the exact details of, is the noise 10% higher or the noise 10% lower. If the noise is 100% higher or lower, that will often make a big difference. But when I'm training a model for a helicopter or something, the noise is something that I pay a little bit of attention to, but I pay much more attention to making sure that the matrices A and B are accurate. And then if a little bit of sloppiness in the accuracy of your noise model is something that an MDP could probably survive, that your policy could survive. Okay, let's take one last question. Then we should. Oh, V. B. Oh, I see. Sorry. Yes. Let me see my notes. V. That was a B. This is a V. Yes. Thanks. Yeah. Okay. Cool. Thanks, everyone. Let's break, and then we'll see you for the final lecture on Wednesday. Thanks, everyone.